Hello, Algebra 2, and welcome to Lesson 6.4. We're going to talk about logarithmic functions, the graph of the logarithmic function. So our essential question today is, how is the relationship between logarithmic and exponential functions revealed in the key features of their graphs? So let's first look at the graph of log base 2 of x. And Salas actually has this really nicely graphed, right? When we're going to look at this blue one is log base 2 of x. And we're kind of also looking, not only just answering the question, but also looking at the relationship between log base 2 of x and its inverse, y equals 2 to the x power. We'll notice that log base 2 of x, right, cannot have any x values that are 0 or negative, and that matches with the graph. But, it can have any x values going way, way out, right? Way, way out. Its restriction is over here. So then its domain is going to be all x, such that x is not negative. Salas has your domain written in set notation there. Right, we could also say that it goes from 0 to infinity using our interval notation that we normally use. That is a bracket there. Make it look a little better. All right. So that's the domain. The range is going to be all real numbers. It has no y-intercept. The x-intercept is over here at, I'm sorry, yeah, at 0, 1, 1, 0, 1, 0. And we can find that right here. We've got a point there at 1, 0 for the log. And you can also see that the graph of y equals 2 to the x power is a reflection of y equals log base 2 of x, the function that we're being asked to graph. So there is an asymptote at the y-axis for our logarithmic function, and for our end of behavior, right? As x approaches 0, y approaches negative infinity, and as x approaches infinity, y is going to also approach positive infinity. Just having a little look at the graph of our logarithmic function. Let's also look at what happens when we do some transformations on these. And I feel like we've looked at transformations so much, we don't need to get too intense with this. If we see, right, that there is some number in these parentheses, we're going to guess that's probably going to be a horizontal translation. And let's look at that. You could just put that in your calculator, right? In your graphing calculator, graph it, compare it to log base 2 of x, and see that it has indeed been translated to the left 3 units. All right, what's happening with this one? Well, I'm going to guess that this -4 is going to translate it to the right 4 units, and this -2 should be shifting the graph down 2 units. Let's see what we've got. There we go. All right, so now we'll get into something that's new, but using the skills that we've learned in the last lesson. We're going to talk about inverses of exponential and logarithmic functions. So how would I find the inverse of this function? All right, so step one, when we're finding an inverse, we are going to let f of x equal y, right? So in other words, I'm just going to write this as y equals 10 to the x plus 1 power, right? So this is all in your exponent up there. All right, number two, now I'm going to let y equal x and x equal y. I'm going to switch them, right? So instead of a y, I'll substitute x. And over here, instead of an x, I'm going to substitute a y. All right, so for step three, now we're going to write it as either an exponential function, an exponential equation, or logarithmic equation. In this case, we're going to write it as a logarithmic equation. I think I'm spelling pancake, or a logarithmic equation. Okay, so we remember how to do that, right? We would say that this is that log base 10, right? I'm not going to write the 10 because it's assuming that it's log base 10 of x is equal to y plus 1, right? Using the skill that we learned in the last lesson. Step 4, solve for y. All right, all we need to do to solve for y in this case is subtract 1 from both sides. And there we have it. It's done. This is the inverse of this function. Okay, let's do another one. So with this one, we're going to follow the steps. But now, when we get to step 3, we're going to write it as an exponential equation. So first step, we're going to let g of x equal y. So we're just going to write it in the form where we have y. And it's log base 7 of x plus 5. Okay, now we're going to substitute x for y and y for x. Now let's write this as an exponential equation. So 7 to the x power is going to be equal to y plus 5. And now we need to solve for y. So 7x, I'll subtract 5 from both sides. And there you have it. All right, and the last thing that we're going to do is apply this inverse to a real life situation, right? So we've got a company that uses this particular formula, R equals 12 times log base 10 of a plus 1 plus 25 in order to relate sales revenue and advertising costs, where sales revenues are, that's the output, right? And the input, the thing that you plug in there is some sort of number value for a cost. We're being asked what is the equation of the inverse of the formula, and which equation would be easier to use to find a value of a for a particular value of r. Let's answer the question. So first thing I want to do, I'm just going to write this r equals 12 times log base 10 of a plus 1 plus 25. And right, we don't have to do the first step where we take the f of x and make it a y. We're going to switch these two variables as our first step. So instead of a, I'm going to substitute, instead of r, I'm going to substitute a. And then instead of a, I'm going to substitute r. Okay, now we've got to get this logarithm by itself. I want this stuff by itself. okay? I want that. So I'm trying to isolate the logarithmic expression. So let's start by subtracting 25 from both sides. And now let's divide both sides by 12 to get rid of this 12 here. All right, so dividing both sides by 12. So that's going to give me a plus 25 over 12 equals log base 10 of r plus 1. And now that we have the logarithm all by itself, let's write it as an exponential expression, right? So remember, this is log base 10. So, and it's kind of weird, but this is 10 to the, this stuff is all in your exponent. A plus 25 divided by 12, right? So this is 10 to the a plus 25 divided by 12 power. Kind of weird. Equals r plus 1. Last step that we need to do in order to have this thing done is just to subtract 1 from both sides. So this is going to become, I'm going to run out of room, so I'm going to write this up here. Sorry about that. This is 10 to the a plus 25 over 12 power, right? And subtracting the 1 gives me a minus 1 there, equals r. And there we go. We have found the inverse. Now, this is great. This is the inverse. But what this is actually asking for is something different. So, when we did this switch here, we didn't need to actually switch those variables. So, what you're actually being asked for is to write this in terms of A. All right, so even though we're following, I showed you how to do the inverse, what this question is actually asking for is something different. It's asking for us to solve for A. So the switch is actually not going to be necessary. So if we solve this for A, we're going to have r minus 25 equals 12 log base 10 of a plus 1. And we'll divide both sides by 12, so we'll have r minus 25. Right, the solution is going to be the same for writing this in terms of A. Right now we've got to write it as an exponential. So that's 10 to the r minus 25 over 12 is going to be equal to a plus 1. And then one last step, 10 to the r minus 25 over 12 minus 1 equals a. And now we've written it in terms of a. So we both did the inverse and wrote it in terms of a. Your book will be looking for this. Yeah. Well, thank you so much for being here, watching, listening. Guys, I hope that you have a fantastic day. And if it's not a fantastic day, man, I really hope it gets better. Take care of yourselves. Bye.